Welcome everyone to this week's algebraic graph theory seminar. Today we have Shahla Nasserasr speaking from Nasserasr Institute of Technology, and she will tell us about distinct eigenvalues and sensitivity.
Thanks, Sophia. So thanks everyone for coming. The timing of this talk is kind of really interesting because 2 weeks ago, Nathan gave a very nice talk on the sensitivity. And then last week, Crystal gave an also really nice talk on the simple eigenvalues of graphs. I believe she was considering the 0-1 adjacency matrices. So this is kind of related to both of them in a way. Here we are going to consider the weighted adjacency matrices instead of the 0-1 adjacency matrices. And I thought Sophia did a really good job on ordering the talks. So thank you for that, Sophia. And before I start, this is a research group. There was a very nice research group at the University of Regina that I was part of it when I was a postdoc there. We started working on this parameter called minimum number of distinct eigenvalues of matrices related to graphs a few years ago. And then later, when I went back to queries, we started working on it again. So this is a combination of those two works. And at some point, I will show how some of the techniques that are used here are also used in the sensitivity. So first I will talk about the inverse eigenvalue problem itself a bit, and then I will talk about some of the sub-problems in that area. Multiplicity is one of them, and among them another sub-problem of the multiplicity problems, which is the minimum number of distinct eigenvalues. So that will be basically the main topic of the course of the talk. And then at the end, I will show you how a technique that's used in one of the proofs for the eigenvalues is also used in the sensitivity theorem. So here we are going to consider simple graphs, which means we have no loops and no multiple edges. And for any such graph, we consider the set of symmetric matrices of the size of the number of vertices of the graph, so that their zero-nonzero pattern shows basically no edges and edges of the graph. So in other words, the ij entry is non-zero if and only if there's an edge from vertex I to the vertex j. So if we consider all these matrices and put them in a set, that set is called S of G. And having that, the inverse eigenvalue problem basically says if I have n numbers, possibly repeated, what are the necessary and sufficient conditions on those numbers so that there is a matrix in S of G for the graph G that has these numbers as its eigenvalues. So another way of asking the inverse eigenvalue problem is that for a given graph G, what are all of the possible eigenvalues of matrices in S of G? So as you can see, it's a really big problem and it has been studied very well. There are lots of really nice techniques and results in this area. I'll just show you a few of them. And the first one is kind of an old result by Fiedler in 1969. That he basically says if you take a symmetric matrix so that by changing the diagonal entries, the rank of the matrix doesn't go below n-1, then that's simply the matrix of a path. And moreover, we can easily show that paths can only take simple eigenvalues, just like what Crystal did last time, but we here have weighted adjacency matrices. And that basically tells us that the eigenvalues of every matrix in the S of G are distinct if and only if that G is a path on n vertices. So basically what this says is that the inverse eigenvalue problem is completely solved for paths. There are some other graphs when the inverse eigenvalue problem is completely solved. Complete graphs is one of them. And there are several proofs for this. I chose the one with Johnson and Zhang because their proof is kind of really simple. So basically what they say is that if you start with a diagonal matrix such that at least two of the diagonal entries are distinct. So not all of them are the same. Then you can perform a bunch of givens transformations so that at the end you get a matrix when none of the entries outside of the diagonal entries are 0. And that's exactly a matrix for a complete graph. So basically what that says is that any set of numbers, as long as at least two of them are distinct, can be the spectrum of a matrix in S of Kn. So that solves the inverse eigenvalue problem for complete graphs too. So I believe the inverse eigenvalue problem is also solved completely for cycles and some other families of graphs, but it's still obviously open. And there are many graphs that we don't know all of the answers for them. So let me mention this nice result here by Monfort and Shader. That says if we have a graph on n vertices, and if we take n distinct real values, then they are going to be the spectrum of a matrix corresponding to that graph. So the authors use the implicit function theorem for this. Basically, they start with a diagonal matrix when all of the diagonal entries are distinct, and they perform the process from the implicit function theorem to perturb some of the entries so that they get any pattern that they want. So what this says is that any set of distinct eigenvalues can be the spectrum of any graph, which is amazing. And that reminds me of what Crystal said last week, that was almost every graph has simple eigenvalues. Again, I believe she was considering the 0-1 matrices. Here, these are the weighted adjacency matrices. No, I didn't get a chance to read the paper that she was suggesting by Tao and Wu, but I don't know if there are any connections here. So these are some of the results between some of the results that are known about the inverse eigenvalue problem. Obviously, there are way more results than I can talk about them in here. I'm just going to talk about some of the sub-problems here for now. So when you think about the inverse eigenvalue problem, the question is, for which numbers can they be the spectrum of a matrix in S of G? So the question is about the values of eigenvalues. Here, we are going to consider the multiplicities of the eigenvalues versus their values. What happens here is that we list the eigenvalues from in an order, let's say from smallest to largest, and each of them might have their each of them will have their multiplicities, either one or more than one. And the question is, which one of those multiplicities can be the multiplicity list of matrices in S of G, of the eigenvalues in matrices in S of G. So this question by itself is a big question. It has been studied, and again, there are many results as well as many open problems. One related question is the minimum rank problem, which is basically what is the minimum rank among all matrices in S of G. And when you think about the multiplicity list, we get a sequence of positive integers for every matrix. So the one question could be that, what is the minimum length among all those sequences? And that's exactly the minimum number of distinct eigenvalues, which is Q of G, and that's what I'm going to talk about in this talk. So Q of G is defined to be the minimum number of distinct eigenvalues of matrices in S of G. And from now on, I'm going to show you some of the results that we know about this parameter. Am I going too fast? Okay. So first of all, I'll show you the relationship between Q of G and minimum rank. So Q, minimum rank plus 1 is an upper bound for Q of G, and that's not hard to see because if I take a matrix that does achieve the minimum rank, Because these matrices are symmetric, I can diagonalize it, and we can write it in this form, which basically has minimum rank number of non-zero eigenvalues plus the remaining eigenvalues are 0. And since we are looking at the distinctness, the maximum number of distinct eigenvalues that we can have in this matrix are minimum rank plus 1, 1 for 0. And because Q is the minimum of all those, Q is going to be at most minimum rank plus 1. So, so that's an upper bound for Q. We also have this nice lower bound for Q that says, it's by Fonseca in 2010, that says if we take two vertices that have a distance d, and moreover, if that path of length d between them is unique, then Q is going to be at least d plus 1. So in other words, if there is a unique shortest path of length d between two vertices, then Q is at least d plus 1. And the proof for it is a very nice linear algebraic proof, so I'll just briefly mention it. So the proof says, just take any matrix in S of G and look at the UV entry of the matrices A squared, and all the exponents of A until D minus 1. Because the distance between them is D, all of those matrices are going to have 0 in the UV entry. And when we get to the D exponent of A, because that path was unique, the UV entry is basically going to be the product of some non-zero entries. In other words, there's not subtraction and there's no addition, so there's no cancellation. So that entry is going to be non-zero, and that gives us these matrices identity A and all the exponents of A to the exponent of D to be linearly independent. So we get a lower bound for the degree of the minimal polynomial, which is exactly Q. So Q is at least D plus 1. So that's a very nice lower bound in a lot of cases. Let me just explain it in this example of what happens. So if you look at the vertices C and E, for example, the distance between them is 2, and there's another path between C and E, which is length 3. So the shortest path between them is unique. So we can use D to be 2. So Q is at least 2 plus 1, which is 3. And it's not hard to show that this graph has Q equals 3. I believe the inverse eigenvalue problem is completely solved for graphs of size at most 5. So we know everything about this one. So that's an example. Now, a question that we might ask ourselves is that bound sharp? And the answer is yes. In this graph, for example, it's a C4 with 2 paths hanging from opposite vertices, the non-adjacent vertices. If we have a path, if the longer path from the pendant vertex to the middle of C4 has a length D, then that's a unique shortest path, and we can show that Q of this graph is exactly D plus 1. So that's one graph when that lower bound is tight. And there's also another family of graphs when this lower bound is tight. Those are hypercubes, which I will talk about them in more details later. But for now, it's not hard to see that D in hypercubes is simply 1, but we will show later that Q of those are 2. So in this case also, Q is exactly D plus 1. So it is a nice bond, and in case of trees, for example, because every path is unique and shortest, we get that Q to be at least diameter plus 1. In this specific example, Q is exactly the diameter plus 1, but of course those are just in the case of trees. So speaking of diameter, I'll just mention that it's not always going to be that diameter plus 1 is a lower bound for Q. And again, hypercubes as an example. So in hypercubes, we know that the diameter is n for the ones with 2 to the n vertices. But later we will see that Q of these graphs is 2. So not only diameter is not a lower bound for Q, but also the gap between them can be quite large. So that's about the some upper bounds and lower bounds for Q. Now I'm going to talk about the question of can we characterize graphs with a given Q. We know that the value of Q is somewhere between 1 and the number of vertices. The question is, if I have any value between those numbers, which graphs do have Q equals that number? So starting with the case of Q equals 1, we see that that's just a trivial case, because if Q is 1, that means all of the eigenvalues are the same. So basically, when we diagonalize, we have a multiple of identity, and that simply means that there are no edges, and the other direction is not hard to see at all. So that's a characterization for the case of Q equals 1, that we don't have any edges. So that case is trivial. The other extreme case is already answered as well by Fiedler, and that is Q is n. In other words, all of the eigenvalues are distinct if and only if G is a path on n vertices. So these two extreme cases are known. And then the case of the number of vertices minus 1 is also known by Barrett, Follett, Hall, Hagman, Lin, and Shader in 2016. That it's a characterization again that graphs that have Q equals n minus 1 are these three, and it's an if and only if condition. So what are these two graphs? The first one is just a pattern n minus 1 vertices with an isolated vertex. The second one is a path on n minus 1 vertices with a pendant vertex in the middle, and somewhere in the middle. And the last one is a path on n vertices with two vertices of distance 2 being connected by an edge. So the proof for this is a bit technical. I'm not going to talk about it, but that says we have a characterization of graphs with Q equals 1, n, and n minus 1. So of course the question is, what about the other values of Q? So let's just start thinking about the graphs with Q equals 2, because that's where it gets really interesting. So first I'm going to show you some examples of graphs with Q equals 2. So a very simple one is just a complete graph. You can just write the adjacency matrix and see that it has 2 distinct eigenvalues, and Q is not 1, therefore it has to be 2. And another example is the complete graphs, complete multi-partite graphs when there are some conditions on the sizes of the parts. And that condition is that we can write the sizes so that sum of the sizes of some of them is equal to the sum of the sizes of the remaining parts. So using the previous results that I haven't talked about them yet, we can show that Q of this graph is 2 as well. So a simple version of this is the complete bipartite graph when the 2 parts have exactly the same size. Then Q is 2, and I'll just mention that we've shown that Q of complete multi-partite graph is either 2 or 3. In this case, it's 2. In the other cases, it's either 2 or 3 again. So that's another family of graphs. And then there's another family of graphs that, in fact, the inverse eigenvalue problem is completely solved for them. That is a complete graph minus the matching. And we can, using their result, we can see that Q of them is 2 as well. And there are many more. I've just listed one more here by Levin, Oblak, and Schmiduk that they say Q of the complement of many trees is 2, basically. What do I mean by many? So if T is not a path on 4 vertices, and or if T is not this graph, which is that SM1K is basically a path with some pendant vertices, M pendant vertices hanging from one end. And so you can think about a star with one of the edges being a path instead of one edge. And the W2L1D is basically a tree, a rooted tree of that 2. So if you take away those, then Q of the complement of all other trees is simply 2. So as you see, there are so many graphs with Q equals 2. And I'll show you one more example. that's very interesting as well. And those are hypercubes. So we all know what hypercubes are. I've drawn them in this shape for a reason. So hypercube is basically starting with a K2 and Cartesian producting it with K2 and then continuing all the Cartesian products with K2. So why have I colored them in this way? Because we want to construct the matrices using these colors. So the way that they're colored is that you start with a color for the first K2, and when you copy that graph to add the matchings between the vertices, you just change the color of the original graph. So the opposite colors will come to your copy. So here I have, I don't know. So here I have blue, the opposite of that is going to be red. Here, this is my C4, and blues become red, reds become blue. And the matching edges are all blue. So that gives us these matrices. And the blues are going to be 1, the reds are going to be -1. So you can think about the constructing of the matrix in this way, that we put the previous matrix in the 1, 1 block, and then the negative of that and the 2, 2 block, and the identities on the 1, 2, and 2, 1 block. So constructing the matrices with this way, we have this nice result. So I'll just mention that in that paper, we actually showed a bit more general result, and that is if G has Q to be 2, then the Cartesian product of G and K2 is going to be 2. But for this talk, I'm just going to apply the exact same proof to the hypercube, because later I will use this in the sensitivity. So start with the K2 itself and write the adjacency matrix that has simply eigenvalues -1 and 1. And then when we construct B2 from the previous matrix, we get that B2 is of this form. So the diagonal blocks are B1 and -1. The off-diagonal blocks are identities. And then when you square it, you see that you get the exact same blocks for the diagonal blocks and zeros on the off-diagonal blocks. And therefore, the eigenvalues of the square of this matrix, in this case, are simply the eigenvalues of the previous matrix squared plus 1. And that gives us the eigenvalues of B2 to be the square root of 2 and minus the square root of 2. And if we continue with this way, we will see that Bn is going to, which is the matrix of the Qn, which is going to have 2 distinct eigenvalues, one to be square root of n and the other to be minus the square root of n. And the key here for the sensitivity is that they have the exact same multiplicities. So square root of n has the multiplicity of the half the number of vertices, and so is the minus square root of n. So that gives us a Q to be 2, of course, but again, that multiplicity is what plays a role in the sensitivity that I'll talk about it later. So this is another example of graphs with Q equals 2, and as you see, we have too many of them. So let me tell you a bit about the structure of graphs with Q equals 2 as much as we can. So if Q is 2, and if I take K vertices that are independent, we can show that the union of their pairwise common neighborhoods is either empty or it has at least K vertices. So if I apply that in this example, if I take 2 vertices that are independent, so C and E, for example, there is no edge between them, then we see that there is only one element in their common neighborhood. So that means the Q of this graph is not 2, because if it was 2, it must have had at least 2 neighbors. So this gives us some other results about the structure of the graphs with Q equals 2. For example, every 2 non-adjacent vertices must have at least 2 common neighbors, or every vertex is in a cycle, or there are no pendant vertices, and so on. So, so those are a bit about the structure of graphs with q equals 2. But then the next result, which is here, is kind of really interesting because it says, so let me mention the statement first. So what it says is that if you take two connected graphs that have the same number of vertices, and if you join them, then regardless of what they were from the beginning, q of the join simply drops to 2. And by join, I mean connect all the vertices of the first graph to all the vertices of the second graph. So for instance, if you take path, which has the maximum number of q's, and join it by itself, then the q of the resulting graph is simply 2. So we showed that for a graph by itself, and then later Montford and Shader showed it for a graph, for any two connected graphs, as long as they have the same number of vertices. And the same number of vertices is important. Like here we have an example that when they don't have the same number of vertices, it's not going to work. So what's nice about this is that it says that every graph can be an induced subgraph of a graph with q equals 2. And that's really nice, but at the same time, it also says that characterizing graphs with q equals 2 can be difficult, because finding a forbidden set of graphs can be really difficult because of the this result. So at this point, it's kind of disappointing if one wants to characterize such graphs. Instead of that, what we did was to look at the graphs with q equals 2, and at the same time consider the multiplicity by partition, which means that we assume one of the eigenvalues has a multiplicity k, and the other therefore is going to have multiplicity m minus k. So we are still looking at the graphs with q equals 2, but this time we are going to consider the assumption that we know their multiplicities, and the question is, can we characterize them? So if you look at hypercubes, that's an example of a graph when it has the multiplicity by partition of half the number of vertices and half the number of vertices. But that's just an example. So we are going to look at all possibilities here. So if we start with k equals 1, that's not a hard case at all, because we can see that multiplicity by partition of 1 and m minus 1 is achieved by a graph if and only if it's a complete graph with possibly some isolated vertices, and it's not hard to see. So that's a characterization and not hard at all. For the case of 2 and m minus 2, this has been shown in several papers in the minimum rank and other topics, that a graph has a multiplicity by partition of 2 and m minus 2 if and only if it's of this form. Now, what is that form? We have two complete graphs of any size union together, meaning do nothing basically. And then two other complete graphs, again, of any size, and union them together, and continue this as much as you like, well, k times, which is not related to 2 really, and then join all of them together. So as long as we don't create a complete graph, or this one, the union of two completes joined with an isolated vertex, it's shown that these graphs are going to have multiplicity by partition of 2 and m minus 2, and those are the only graphs. So these two cases of 1 and m minus 1, 2 and m minus 2 are known. Now, when we look at the 3 and m minus 2 or higher case, 3 and m minus 3 or higher cases, we don't have a characterization for them yet, but what we have is that if we go back to the previous result that had the union of two complete graphs and then join them together, if we replace two complete graphs with k complete graphs here, we can show that those graphs are going to have a multiplicity by partition of k and m minus k. So we do have a generalization of the previous result. However, that's not a characterization because we can show that if we take one of those complete graphs in the previous graph and take a matching out of that complete graph, then Q's is still 2, and with the multiplicity by partition of 3 and then minus 3, and it's not any of the graphs in this lemma. So we do have families of graphs with K and n minus K, but we don't have a characterization for them. So that problem is still open, basically. So that's really all I wanted to say about the Q. Now I'm going to briefly mention about the sensitivity and show you how that hypercubes are used in the sensitivity. So in 1987, Chang, Frody, Graham, and Seymour proved that if you have an induced subgraph of a hypercube Qn that has more than half the vertices, then the maximum degree of that induced subgraph is bounded below by this logarithmic function. And they also showed that there is an induced subgraph of G of the hypercube such that the maximum degree of that induced subgraph is at most the square root of n plus 1. So, from my understanding, they thought that this upper bound is actually far from best, and they thought they could improve it. So having that in mind, let's just briefly look at the sensitivity. Again, Nathan did a really good job on talking about the sensitivity 2 weeks ago. So, sensitivity is about the Boolean functions. And we have the local sensitivity, which is basically the number of positions in an input X, such that by changing the value of those positions from 1 to 0 or 0 to 1, the value of the function will change. And the sensitivity itself for the function f is the maximum of all those local sensitivities over all inputs. And we have the local block sensitivity, which is the maximum number of disjoint blocks when changing the values of positions of the entire entries of blocks will change the value of the function. And again, block sensitivity is the maximum of all local block sensitivities when maximum is taking over all inputs. So having these, Nissan and Judy in 1992 conjectured that the block sensitivity is bounded above by a constant exponent of the sensitivity of the function. So this inequality is obvious to see because of the blocks can be of size 1, but this one was open for a while. For quite a while, actually. So in 1992, Gottsman and Lineal showed that the sensitivity conjecture at the time can be reduced to the question that Chang and her co-authors had in 1987. And they also conjectured that the square root of n is the best one. So this was open all the time until 2019, which is when Hang gave this really nice proof of the sensitivity. So I've outlined that in here. That basically says the hypercubes have 2 distinct eigenvalues and with the exact same multiplicity. So the rest of it is just basically linear algebra. Because if you take a principal submatrix of size at least half the size of the matrix, then that's definitely going to have a square root of n as its eigenvalue. And because these matrices have only entries from 0, 1, and minus 1, it's not hard to see that the maximum lambda is going to be at most the maximum degree of the graph, and that gives us the bound that we want. The square root of n is at most delta. So Hang proved this. I had no idea about the sensitivity conjecture until then. And since then, I've seen several nice or shorter proofs. And I'll show you one of them because it's also a really basic proof. It's using some elementary linear algebra. The exact same statement, but a different proof. So what they do, by the way, that is my brother who was a postdoc at Waterloo at some point. So what they do here is that take a matrix in S of Qn such that it has entries 0, 1, minus 1, and assign those entries so that every 4 cycle has an odd number of ones and odd number of minus ones. And that's easily can be shown that it is possible to find such matrices for every P1. And because of the structure of the matrix, A squared is simply going to be n times identity. And therefore, we have this nice relationship between the A plus square root of n times identity and A minus square root of n times identity. So what that means is that the row space of A plus square root of n times identity is orthogonal to the column space of the other matrix. And because these are the subspaces of the R to the number of vertices, which is 2 to the n, one of them is going to have dimension at most 2 to the n minus 1, the half of the size. Sorry, the half of the dimension. So what that means is that when you look at the rows or columns of one of these matrices, and if you take more than half dimension, then there's going to be a linearly dependence relationship between them. And all we have to do is to write that linearly dependence relationship and look at the vertex with the largest coefficient. And it's not hard to see that that vertex is going to have at least the square root of n neighbors. So I found this proof, and there are some others as well, using just eigenvectors, not eigenvalues anymore. Kind of really quite interesting, especially that the conjecture had to wait for so long to be solved. So that's really all I wanted to say. There are lots of open problems in this area, such as characterizing graphs with a given cube or those that we don't know, or characterizing graphs with a given multiplicity by partition for those that we don't know. And since the sensitivity, I've been interested in finding graphs when they have a multiplicity by partition with exactly the same multiplicity for both eigenvalues. And again, there were some nice proofs using just the eigenvectors for the sensitivity theorem. That would be nice to see which one of these proofs can be improved using the eigenvectors as well. So that's all I wanted to say. Thank you.
Thank you, Shahla. Do we have any questions?
I have a question.
Yep.
So the multiplicity problem seems to be pretty closely related to the Colin de Verdier parameter. Is there some sort of like nice, so there's a sort of like geometric explanation for what the, for the Colin de Verdier parameter in terms of like a transversal intersection of manifolds? Is there some sort of nice geometric explanation for what's going on in the multiplicity case?
In a multiplicity case, I don't know multiplicity, but I know that there are lots of connections. Sean would be a better person to answer that. I think it's here.
I can respond if you want.
Yes, please.
So there is a property analogous to the Strong-Arnold property referred to as the strong multiplicity property, which is in that same vein where as long as two manifolds intersect in the right way, then you know, if a graph is a minor of another graph, you can preserve the multiplicity lists as long as you allow a certain addition of simple eigenvalues. So there are geometric associations, as you noted. Yes.
Okay. All right. Thank you.
Thank you, Sean.
Yep.
I have a question. So this could be about any of the cases where you or someone has shown that the Q equal 2 holds. I'm wondering what, if in any of the cases other than the hypercube, if the weightings are integer valued, are they ever as nice as they are in the hypercube case?
You mean the entries of the matrix are integer values?
Yes.
I think that limits a lot of these results because in most of the cases, as far as I know, we use the diagonal entries being free.
Mhm.
So I don't know how that will affect us. There are lots of studies in that, like Seidel matrices or universal matrices, all studied separately. But I haven't worked on them in detail. And in some of these, especially when Q is 2, we use the orthogonality a lot. And that's because we can shift the diagonal entries so that you get 1 and -1 as eigenvalues. So I don't know if that could be applied when you eliminate the freedom of diagonal entries. Again, Sean could be.
I mean, it's natural to sort of start with things that have rational entries just because that's the easiest thing to deal with. But once you invoke things like the implicit function theorem and so forth, and you start perturbing, there's no real hope. I mean, the hypercube works nicely because of the natural product structure of graphs, but in general, things are pretty wide open.
Mhm.
Do we have any other questions? I guess I'm just curious what you have these open problems in the at the end. Are there specific ones that you're working on currently?
I am thinking of the third one, but I haven't made much progress.
Okay. I see.
Well, in fact, this semester I haven't made much progress in any research because I just moved to Rochester this year.
I see. Yeah.
Could I ask a question?
Yes. Hi, Aidan.
Yes. Hi. So can that construction for the hypercube be generalized to, you know how with the hypercube you start with K2 and you take Cartesian product with K2 itself, right? Can you generalize it to K3 or K4 or like other Hamming graphs?
Oh, you mean Cartesian product with K2?
Like K3 with itself, for example, or K4 with itself?
I have no idea.
Okay.
That's a really good question. But, yeah, I don't know. I'll have to think.